So, okay, we can start with our last seminar, and the first speaker is Jeroen Monnee from Utrecht University, talking about complexity of the Flux landscape. Please.
Okay, great. Thank you. Thank you all for being here. And of course, thanks to the organizers for giving me the opportunity to present in this seminar. So today I will talk about some recent work I did together with my supervisor, Thomas Grimm, which in a broad sense is about the complexity of the Flux landscape. And I will explain what I mean by this, of course. But first, let me give you some general motivation. So I'll be talking about effective field theories that arise from string compactifications. And in this setting, we always have to deal with moduli. And the way we deal with them is by trying to stabilize them at the minimum of some scalar potential, which I denote by V. So it depends on the moduli, and it can depend on additional parameters that depend on the UV theory you consider. So for me, these parameters will be fluxes. Now, for some values of these parameters, you might indeed be able to stabilize your moduli at some particular points in the moduli space. For other values, you maybe get some different vacua. It could also happen that for some values of the parameters, you cannot stabilize all moduli, and you are left with some higher dimensional components of the vacuum locus. You have a flat direction in the potential. So this raises many questions, which all have many of them have been raised before in the literature. Sort of a very coarse question is to ask about finiteness, whether if you range over all the possible values of the parameters, if you get a finite number of vacua. A finer question, if you do have a finiteness, is how many vacua are there? How can you count them? How many of these have flat directions? When do they have flat directions? And can you say something general about the complexity of the landscape as a whole in such a way that it is computationally useful? So today I will argue that in at least the F-theory setting, you can make some progress in this direction to answering these questions. And the reason you can do so is because this potential is far from something generic. This potential comes from geometry. And when it comes from geometry, you have tools which you can use to analyze these questions. And I will talk about the tools of Hodge theory and minimal geometry or tame geometry. So that brings me to the outline of the talk. So I'll first review some basics of the F-theory landscape and some finiteness results that have been obtained in this context. And then the majority of the talk will be devoted to what I would call refining the Flux landscape, by which I mean addressing these finer questions I mentioned by motivating three conjectures, which sort of answer partly these questions. And then I will conclude. So the nice thing about giving a landscape talk is that you get to include some nice pictures of landscapes. So here's one picture of what maybe the F-theory landscape could look like pictorially. So I will consider F-theory compactified on an elliptically fibered Calabi-Yau fourfold with fluxes. Flux I denote by G4, it will be some cohomology class. And this flux has to satisfy two consistency conditions. The first is that it is half integer quantized, quantization condition. And then there is this condition which gives a bound on the self-intersection of the G4 flux in terms of the Euler character of the Calabi-Yau fourfold, which is known as the tadpole cancellation condition. Now, after doing the compactification, you will be left with some 4D n equals 1 supergravity theory, which in general will contain many different fields. But the fields I will focus on today are these complex structure moduli of the Calabi-Yau, which I denote by Zi. And indeed, these complex structure moduli get a potential which is induced by this G4 flux. So this potential looks as follows. So up to some volume factor of the base, it is given by the integrated kinetic energy of the field strength minus some topological term. And the global minima of this potential are given by configurations where this G4 flux is self-dual. So star of G4 is equal to G4, where I remind you that this star is what induces all the moduli dependence, because it depends on the metric of the Calabi-Yau. For those of you who are maybe more familiar with the superpotential formulation, this is the same as saying that the Kähler covariant derivative of the superpotential has to vanish, where this W is the standard Kukel-Fafa-Witten superpotential, and the Kähler potential is just a tree-level one. So I will not be considering any corrections to these. So in principle, this is the whole class of vacua I will consider in this talk, but I want to mention one sort of particular subset of these vacua which are especially nice. These are the ones which additionally satisfy W equal to 0 in the vacuum. And on the Hodge theory side, this is the same as saying that this G4 flux has to be of type 2,2 in the Hodge decomposition. That means it's an example of a Hodge class, And these Hodge classes are very special. They play a very important role in Hodge theory in general, as I will also explain later on. So this is the whole setting I will consider today. And now I want to sort of review some results on the finiteness of this part of the landscape. So I find it very amusing that already before the landscape really came to be, there was already a math result, which essentially states that the number of W equal to 0 vacua is finite. So this is a very famous theorem by Catani, Deligne, and Kaplan from 1995. I would say it's one of the most important theorems in Hodge theory at the moment. And here I've written down sort of the simplified version of this theorem for the Calabi-Yau fourfold case. So it essentially says that if you look at the set of all complex structure moduli and G4 fluxes, such that this G4 is a Hodge class with a bounded self-intersection, right? So that means that it satisfies this equation. And this set turns out to be an algebraic variety. So roughly that means that it can be obtained from the zero locus of some finite collection of polynomials. And this is amazing because this in particular means, because this zero set can only have finitely many connected components, that you immediately obtain the finiteness of W equal to 0 vacua. But I want to stress that somehow this result is much deeper than this, right? So the fact that it is algebraic is really remarkable. If you have some experience working with period integrals, for example, you will know that the equations you are trying to solve are very nasty transcendental equations. Somehow on this locus, it all reduces to something algebraic. So even after going through the proof, I still really, I'm really baffled by this result. However, this result only applies for W equal to 0 vacua. So the question is what happens for general self-dual vacua. And this was addressed recently by three mathematicians, Bakker, Snell, and Zimmermann, in collaboration with Thomas Grimm, where they show a statement which looks very similar. So they show, again, that the set of all complex structure moduli and G4 fluxes, such that now this G4 is self-dual with a bounded self-intersection. They show that this set is tame. More precisely, that it is definable in the O-minimal structure R on X. I don't have time to really go into the details of what this tameness all means, but intuitively you can think of this as saying that this set is somehow generated in a precise sense by expressions of this type. So now you allow not just for polynomials, but polynomials which also involve arbitrary restricted analytic functions and exponentials as well. So I want to stress that this locus can be much more complicated than the W equal to 0 one. But what is amazing is that sort of this whole tameness story is built in such a way that it does retain this finiteness property. So you can really show that also for sets of this type, you can only have finitely many connected components, and this proves that the number of self-dual flux vacua is finite. Okay, if you're interested in this, we also review as part of these theorems in our paper, also some of the proofs. And one thing we do in the paper as well is we try to give a slightly different perspective or another perspective on this using the tools of asymptotic Hodge theory. So from this point of view, the main difficulty is to show that you cannot have infinite tails of vacua that approach the boundary of the moduli space. And then the strategy is to try to analyze your conditions, so this self-duality condition, explicitly within an approximation that gets better and better the closer you go to the boundary. And so one of the technical things we do in the paper is we make some major technical advances in the computation of Hodge norms, in particular in computing subleading corrections. And we show that the properties of these corrections are precisely such that you can forbid these infinite tails from happening also in multi-moduli cases. So since this is a very technical analysis, I won't say too much about this, but I want to point out one thing which I think is important. Namely, in order to make this argument work, it's really crucial that you go beyond what we would say is the leading order approximation, which goes under the name of the SL2 orbit approximation. And going beyond this approximation really requires you to include an infinite series of corrections, which are determined by this seminal paper of Catani, Kaplan, and Schmidt. And there's a procedure to do this. And you can think of this as some multivariable generalization of what I did in a paper together with Thomas and Damian 2-3 years ago. The reason I want to mention this is because a lot of the literature, at least the physics literature that uses asymptotic Hodge theory, has really focused a lot on this SL2 orbit approximation. But now we really understand also a lot about the sub-leading corrections as well. So I think it would be very interesting to revisit some of these analyses with this new knowledge we have. So in particular, you can revisit this classification of F-theory scalar potentials. You can look at the Greek gravity conjecture for D3 particles. Recently, there was work on asymptotic accelerated expansion. And as an example of this, in the paper, we discuss a bit how you can do this generalization for the Greek gravity case. So if you're interested, I highly recommend you to have a look at this. Okay, so this is all I wanted to say about finiteness and a bit about this point of view of asymptotic Hodge theory. Now I want to go to sort of the main part of the talk, which is about these more refined questions that I posed in the introduction. So I want to start by talking about the counting of vacua, in particular the counting of W equal to 0 vacua. So I mentioned already that these vacua are very special. And one way to see that they are special is, well, simply because you are finding solutions to an overdetermined system. Right? So because of this extra constraint, you have one more equation than you have unknowns. And so you would expect solutions to this to be very rare. Geometrically, this is captured in the theory of unlikely intersections. And more number theoretically, basically you're asking, when do there exist algebraic relations among transcendental functions? And this goes a bit into the direction of the Shanoa and Arxiv conjecture, just to give you some keywords to look up if you're interested. Now, what this means for us is the following. This is how I would think about it. So you start with the vacuum equation, dw equal to 0, and you formally try to solve this for the moduli in terms of the fluxes. And then you take this result and you put it into this remaining w equal to 0 equation. And then you're basically left with some highly transcendental equation, which only depends on the fluxes. And so you need to solve this equation over the integers. So pictorially, you have some codimension 1 hypersurface inside the flux lattice, which I depict here by this blue curve. And you're asking, when does this curve exactly intersect an integer lattice point? And somehow the intuition is that this should happen rarely. And then there's a theorem which makes this intuition precise. This is called the Pila-Wilke counting theorem. And I would say it's really one of sort of the pillars of tame geometry as a whole. I think many of the big proofs in this business use this theorem, really. So the theorem says the following. In words, it states that the number of lattice points in the transcendental part of a tame set grows sub-polynomially in the height. So when you're talking about integers, this height just means that you're talking about counting lattice points inside some ball of radius L, say. And then the statement is this number of contained lattice points is less than any positive power of L to some power epsilon with some constant in front. Okay, and I really want to stress that, of course, this theorem is not true for any set. It's really important that it's a tame set. But as I mentioned earlier, we know that the locus of self-dual vacua is tame. So it's not unreasonable to think that this result maybe extends to, say, the counting of W equal to 0 vacua. And this is the first conjecture we write down in the paper. And here I present for you a simplified version of it, particularly for the Calabi-Yau fourfold case. So what we say is for generic, and I come back to this, for generic Calabi-Yau fourfolds, the number of connected components in the set of, well, again, these Hodge classes with now a fixed self-intersection, and the number of components grows sub-polynomially in L. So the precise statement is that for every epsilon bigger than 0, there exists a constant c such that this number of connected components is bounded by a constant c times L to the power epsilon. Okay, so for example, it could grow logarithmically. That's an example that would be allowed. Now, what do I mean by this word generic? So intuitively, what I mean is that you should include sort of special product spaces where, say, the holonomy of your fourfold is not the full SU4, but something else. So for example, it could be a Y3 times a torus or a K3 times a K3. More precisely, in the paper, we make a better formulation where we formulate the conjecture for a general variation of Hodge structure. And then this genericity assumption is replaced by the condition that the so-called level of the Hodge structure has to be at least 3. So this level is a rather intricate definition, so I don't want to say too much about it here. But roughly speaking, this level is a measure for how complicated your Hodge structure is. And in particular, if you have a product space like this, then the level will correspond to the level of the simplest component. So in this first case, the level will be equal to the level of the torus, and for the torus, it's just 1. And it turns out that for the K3 surface, it's also equal to 1 as well. So that's how these two cases are excluded by this condition on the level. But if you have, let's say, a sufficiently generic Calabi-Yau fourfold, then this level will indeed be at least 3. Now, I want to make one final comment about comparing this conjecture to known results on the counting of W equal to 0 vacua in type 2b orientifold compactifications. So there was already some earlier work on this. Also recently, there were some complete counting results. And here you typically find that the scaling does grow polynomially in L. Of course, this is not in contradiction because it doesn't satisfy this level condition. But I want to emphasize what the difference is. Namely, in type 2b, this transcendentality argument I gave, or motivation I gave, doesn't really apply, because in type 2b, you only take into account the axiodilaton to the polynomial level. So sort of by hand, you remove all the exponential all the transcendental corrections you have. So that's why the argument doesn't really work there. Okay, but so to summarize this part, basically we are saying that the counting of W equal to 0 vacua in F theory is perhaps, it scales slower in the tadpole than you might have imagined naively. Okay, so now I want to move to the second question I posed, which is about when are there flat directions? And this, of course, goes into the direction of the tadpole conjecture. So for me, the tadpole conjecture sort of consists of 2 steps. The first step is to ask yourself, what is the value of this pairing when all moduli are stabilized? And naively, you might say that you can make it any value you want. But what the authors of this paper suggest is that actually if there's a large number of moduli, so h3,1 is large, then this number should somehow scale linearly in h3,1, which is the first part of the statement. And then the second part of the statement is to realize that if you also compare this to the scaling of the actual bound you have to satisfy, then depending on what the value of alpha is, it might not be possible to actually stabilize all moduli within the bound. But for the rest, I want to focus on the first part of this argument, right? Because in spirit, what it is saying is that fluxes with a small tadpole cannot stabilize a large number of moduli. And what we do in the paper is we formulate a version of the conjecture, this part of the conjecture, which we think should be valid beyond just Calabi-Yau, which should apply to any variation of Hodge structure. And we try to formulate it in a mathematically precise way. But one thing we do is we do restrict the conjecture in the sense that we only restrict to Hodge classes, so these W equal to 0 vacua. One reason for this is that I think it's perhaps more likely that the conjecture is actually true in this case, but also you just have more tools to actually attack the conjecture. So I would say as a first step towards proving the tadpole conjecture as a whole, I think this is a very a good avenue to approach this problem. So the precise conjecture we write down is the following. So we say, consider a variation of polarized Hodge structure of weight d, which for the fourfold is just 4. Then you fix a positive integer L, and we write E Hodge L for the set of all Hodge classes with a bounded self-intersection by L. And then we conjecture that for certain positive constants C1 and C2, which are independent of L and the dimension of the moduli space, the following statement should hold. Namely, if the dimension of M is sufficiently large, or larger than the C1, and the self-intersection is sufficiently small, measured by this constant C2, then every connected component of this Hodge locus should have strictly positive dimension. So you cannot have any points, and you must have a flat direction at least. You cannot stabilize everything. Okay, and then in the fourfold case, the expectation is that this constant C2 should be of order 1, but in the general case, I'm not sure what to expect. I think it would be quite interesting to see what would happen in the general case. And I want to highlight that this conjecture is actually very interesting for mathematicians as well. because it gives a criterion for when the Hodge locus does not contain any points. And this is interesting for mathematicians because this is somehow the case that is the most difficult to deal with when you have points in the Hodge locus. So for example, there was a recent paper here by Baldi, Klingler, Ulmo, which proved some very deep finiteness results for Hodge tensors, which are like generalizations of Hodge classes. But they can only prove it if you exclude the points somehow. And in fact, we have had some communication with some mathematicians, in particular with Bruno Klingler, and he has proposed some ideas that you could perhaps prove this conjecture in some specific settings if you, for example, assume the Hodge conjecture. So I think this is very exciting. There's many ideas floating around, and yeah, I think this is a good way to try to tackle the tadpole conjecture. Now, for the last conjecture I want to go beyond just this class of special W equal to 0 vacua. I want to say something about all self-dual vacua. Now, like I said, we know that the self-dual locus is tame, it's definable, but this by itself doesn't say that much. In general, I find that with tameness, it's sometimes difficult to really make quantitative statements. But very recently, there has been some very nice refinement of tameness, or minimality, by Benyamini and Novikov, which is called sharp or minimality, and it precisely addresses this point. So let me try to explain very briefly. So if you look at the possible one-dimensional tame sets, you basically just have finite unions of points and intervals, but there's no bound on how many points or how many intervals you could have. So now the idea is to associate or assign a so-called sharp complexity, FD, to positive integers to a set in such a way that it reflects its geometric complexity. So what that means in 1D is that the number of connected components should be bounded by some polynomial that depends on this f, which is called the format, and it's a function of d, which is the degree. So for example, for polynomials, this d is really the degree of the polynomial, and this f is the number of variables, but in general, it's a bit more complicated than this. And the whole construction of sharp minimality is about extending this to higher dimensions in such a way that everything is well behaved under all logical operations. And if you're interested, I invite you to have a look at this paper by Thomas, Lawrence, and Mick, where they also apply this notion of sharp complexity in some quantum systems. Now, what does it mean for us? Well, if on the first sight, you would say, but there's a problem. This O-minimal structure R on X is actually not sharply O-minimal. In a sense, a general restricted analytic function can be too complicated to be captured in this structure. But actually, it's now conjectured that periods are, in fact, definable in a sharply O-minimal structure. So the picture should be a bit like this. So we are in the green part. And it's natural to think that this result should then extend to the self-dual locus. So we conjecture that this locus of self-dual flux vacua is in fact definable in a sharply O-minimal structure. Now you make a proposal for how this degree and format depend on the tadpole bound in the number of moduli. And the main reason this is useful is because, well, this whole business of sharp O-minimality is constructed in such a way that if you know what the f and d is and you know what your O-minimal structure is, then in principle it gives you bounds on the computational complexity of any logical statement you can build. So in particular, it gives you a bound, it could give you a bound on the counting of self-dual vacua, which is mathematically precise. And in a sense, if this is the correct degree and format, then this would formalize the counting results of Ashok, Denef, and Douglas. But it could also be that it refines it, which I think this is a very interesting possibility for the counting of vacua using these techniques. Okay, I'm almost out of time, so let me wrap up. So as a sort of summarizing statement, I would say that the dimensionality and the geometric complexity of the flux landscape. Of course, there are many future questions. You could, of course, try to find proofs. Conjectures we propose. scans of the F-theory landscape of these W equal to 0 vacua. What happens if you include corrections to this? How many of the results I state do you still expect to be true in some approximation? I don't know, but I think it's worth revisiting. And then I also want to recall that I mentioned that there are improved results for computing corrections in asymptotic Hodge theory may also have many, many other applications as well. And with that, I thank you for your attention.
So thanks a lot, Jeroen. Now we have time for a question. Yes, Arthur.
Yeah, so I have a question. Thanks, it was very interesting. I have a question concerning your statement about the difference between F-theory vacua with W equals 0 and type 2B. So did I get you right that basically you're seeing that non-perturbative G-string corrections remove a majority of the W equals 0 vacua that people have found in Calabi-House? Is that the correct statement?
Right. So how I would formulate it is that I don't say it removes it per se. So it could still be a vacuum, but in the F-theory side, it will not be exactly W equal to 0 anymore.
I see. Okay, thank you. But you still have many of those vacua. Is that true? I mean, you still have as a positive statement, not a bound, but does F-theory still have a large number of W equals 0 vacua?
So, I mean, what we propose in the conjecture is that, well, this number of W equal to 0 vacua should scale sub-polynomially in the tadpole. So, for example, it could scale logarithmically. Whether you call that a large landscape, that's up to numerology.
No, but this is a bound. You're proposing a bound. I wonder whether there are positive examples known to support, say, a lower bound. There's a number of vacua cannot be. I see.
Off the top of my head, I'm not immediately aware of results on lower bounds, right? Because to my knowledge, there's been no fully explicit, complete counting of vacua for really a full F-theory model, right? There's this recent work by Erik and Lorenz in the type 2B setting. I don't know if this question.
Not sure if it's just for me, but I don't. It's frozen, right?
I can't hear him either. So I think probably.
Okay. Okay. Okay, because we had other two questions, but if the speaker, okay, Jeroen, are you there? Because you were frozen. Yeah, your connection apparently is not working best.
I think I'm back now.
Okay, you're back now. So maybe we go, we have other two questions, one from Jose.
Hi, can you hear me?
Yes.
Yes.
Thanks a lot for the talk. It's a very naive question. You are showing that even if W naught is non-zero, then there might be some finiteness of the number of vacua. If I now allow to compactify on curved manifolds, then I know I can get infinite families on vacua. There is some other notion of finiteness. Do you have any thought of what makes them different? So different these two setups?
Oh, that's a very good question. Yeah, to be honest, I don't have a clear answer to this. No, for example, for me, these, say, the DGKT vacua are quite puzzling, right? Because in a sense they have infinitely many vacua as well. So, yeah, I'm not sure. I think it would be very interesting to make this connection more precise.
Okay, thank you.
And we have the last question from Monkey.
It's a good question.
Great. Thanks for the nice talk. I have a follow-up question that for the author's question. So one thing that I'm really confused about is that in the last year I proved that if you have all 7 brane configurations have SOA gauge groups, there cannot be any d-1 instanton corrections to the flux superpotential. So in that case, what I would expect is that all the 7 brane all the flux vacua that I find in type 2B should live to the F-theory vacua because there is basically no difference between the superpotential between type 2b superpotential and the F-theory superpotential. In that regard, it sounds really confusing as to how the type 2b flux vacua, the number of them can be smaller than the you know, the F-theory flux vacua. Can you comment on that?
Or is this your statement that really the superpotential is exactly the same? So there are no corrections in the string?
Yeah, at least the flux potential is exactly the same, and then I proved it using Picard-Fuchs equation. So it is rather surprising that there can be, the number of them can be different, unless you're also assuming that your counting includes type 2b flux vacua with non-trivial 7-brane configuration. Then I could totally understand that the counting that you're doing can capture that some non-productive corrections to flux vacua with non-trivial 7-brane configurations might be destroyed.
I see. Yes, thank you for mentioning the paper. I don't have any concrete thoughts on it right now, but I will think about this for sure. Thanks a lot for mentioning it. Yeah.
Okay, so let's thank again Jeroen. Thanks for the nice talk. And now we